Okay, welcome to the lecture today. So I thought we would go through test two from last year, from the class from last year. So again, remember, because this year is different from last year, we're going to have an open book test, and the time allowed is going to be slightly longer. So the test will be also slightly longer, right? So this is not going to this lecture today is not going to obviously be exactly what's in the test, but it will give you a good idea of the types of questions that we ask. Okay, so wow, okay. This test is covering questions from units 3 and 4, which is the Laplace transform. And if I scroll down enough, solving systems of linear ODEs, homogeneous and non-homogeneous. Okay, so let's get into it here. The first question is, use the properties of the Laplace transform to find the Laplace transform of t times cosine t. Okay, so, well, again, what I'd really like you to remember is to have your table of useful information handy when you are doing these tests, okay? So let's just go check that really quickly now. Table of useful information. So here in the table of useful information is the table of Laplace transforms. And there are two things I want you to note for this problem. The first is the Laplace transform of cosine of k of t is s over s squared plus k squared. So in our case, k is just 1, right? So that's pretty easy. So that's number 8. So let's write that down. So let's say the Laplace transform of cosine of t is just quite simply equal to s over s squared plus 1. That was table number 8, k equals 1. So again, I'd really like you to include this information in here because it tells me where you've got the information from, and not that you've just used some other outside resource, which you are not supposed to do for the tests. Okay, well, but we don't have the Laplace transform of cosine t. We have the Laplace transform of t times cosine t. So I just want to go back to my useful information and notice that above that table is this differentiation of transform property here. So if I have a function f of t and I take the Laplace transform of t times f of t, I get negative the derivative of f of s, where f of s is the Laplace transform of f of t. So, therefore, I can say the Laplace transform of t times cosine of t is equal to negative the derivative d by ds of s over s squared plus 1. Okay, well, what is that? Well, I get negative d by ds of s times s squared plus 1 to the power of negative 1. Again, you can use the quotient rule if you prefer it, but I just prefer the product rule, so I always just turn this into a product rule problem. Okay, so if I do that, I can differentiate 1 by 1, s squared plus 1 to the power of negative 1, plus s times negative 1 times s squared plus 1 to the power of negative 2 times 2s. And if I simplify that, I get negative 1 over s squared plus 1. Okay, what have I got here? I've got an s here. I've got a 2s here, so that's 2s squared. I've got a negative 1 and a negative 1 here. So I get plus 2s squared over s squared plus 1 squared. Okay. That one, so that one is fairly straightforward, I think, and I hope you'll agree it's fairly straightforward. Great. All right, moving on then to the next question. I guess one more thing I could say about this one is that you could actually simplify this more if you wanted to, but well, there's no problem with leaving it as it is here, actually. Okay, so moving on to B now, 1b, use the properties of the Laplace transform to find Laplace transform of e to the minus t times t cubed. So already I can see, because I'm multiplying something by e to the at, where a is -1, I can already see that this is going to be a first translation problem, a first translation theorem problem. So the first thing I'm going to do is just look at the Laplace transform of t cubed. Okay, and I know that this is equal to 3 factorial over s to the power of 4. Well, 3 factorial is 3 times 2 times 1, which is 6, s to the power of 4. And I knew that because I checked my table, of course. And somewhere in here we have t to the power of n, number 3 here, with n, so n factorial over s, n plus 1. So we have n equals, what do you have? What was it? 3. Yeah, n equals 3 in this case. So table number 3. So let's add that information for the marker. So table number 3, n equals 3. Okay, so if I know that the Laplace transform of t cubed is 6 over s to the power of 4, then the Laplace transform of e to the minus t times t cubed, well, wherever I see an s here, I'm going to replace it with s minus a, where here a is equal to -1. So this is going to be 6 over s minus a, -1, so it's plus 1 to the power of 4. That was the first translation theorem. Okay. And again, in your test, I really hope that you'd include all these informations. Okay, well, B was pretty easy, so let's move down to C now, if I can get my tablet to work. Use the properties of the inverse, use the properties of the Laplace transform to find the inverse Laplace transform of s plus 1 over s minus 1, s plus 2. So, okay, the first thing I would note here is that we have a ratio of polynomials. On the numerator, we have a first order. On the denominator, we have a second order. So let's write this as s plus 1, s minus 1, s plus 2. So using partial fraction decomposition, I have this relation, right? Let's multiply through by the denominator here. So we have s plus 1 equals a, s plus 2 plus b, s minus 1. Okay, so very similar to all the other partial fraction decomposition problems we've done in this class. Okay, and then let's choose s equals 1 here. If I do that, the left-hand side, s plus 1 becomes 2. A, 1 plus 2, plus b, 1 minus 1, which of course is 0. So we get 2a equals 2, or in other words, a is equal to, oh, I've made a mistake. I get 3a is equal to 2, because 1 plus 2 is 3. Well, that's basic maths. So a is 2/3. Easy. Now we're going to use s is equal to -2. Okay, so the left-hand side is -2 plus 1 is -1. The a term cancels, right, because we get a times -2 plus 2, so this is 0. Plus b, -2 minus 1. Okay, so we end up with -1 equals -3b, or in other words, b is 1/3. So that allows me to rewrite my Laplace transform. So the inverse Laplace transform of s minus, was it minus 1? Oh, plus 1. S plus 1 over, what was it, s minus 1, s plus 2. That is equal to the inverse Laplace transform of a is 2/3, so 2 over 3 times 1 over s minus 1, plus b, which was 1/3, times 1 over s plus 2. So again, because the Laplace transform is linear, I can write that as 2/3 the inverse Laplace transform of 1 over s minus 1 plus 1/3 the inverse Laplace transform of 1 over s plus 2. And again, by now you should be recognizing that these are going to give me exponentials here. So I'm going to get here 2/3 e to the t plus 1/3 e to the minus 2t. That t is a bit funny looking. Let's rewrite that. Okay. So again, if you know your Laplace transforms, well, if you don't, refer to the table, but if you know them, then you can solve these fairly quickly. And, well, whenever you see a problem like this, you're going to think partial fraction decomposition. Okay, moving on to the part, what is this, part D now. Use the properties of the Laplace transform to find the inverse Laplace transform of this thing. Okay, so the first thing I notice about this problem is this e to the minus 2s thing. So I already know, because of that term, this is going to be a second translation theorem problem. Okay. So the first thing I'm going to do is ignore that exponential. Okay, so the first thing I'm going to do is I'm going to look at the inverse Laplace transform of 1 over s minus 1 squared plus 2 over s squared plus 4 plus 1 over s. Okay, so I'm going to ignore the exponential for now. Okay, so these are actually fairly easy inverse Laplace transforms to find, right? So, well, this first one here, if I did not have this minus 1 in here, then this would just be the inverse Laplace transform of 1 over s squared, which is t. Okay, so this would be something like t. But because I have the minus 1, I know that I can use the first translation theorem to write this as t times e to the t. Okay, so that's this term here. The second term here, well, this is, I can already see that this is a sine with k equals 2. So this is going to be sine of 2k, 2t. Hang on, sine of 2t. Let's write that again. Okay, so because remember, sine of k times t, the Laplace transform of that is k over s squared plus k squared. So if k equals 2, I get 2 over s squared plus 4. Okay, and 1 over s, this last term here, well, okay, it was this term. This last term here, well, I may recall that the Laplace transform of a constant was just the constant over s. So this is just plus 1, in fact. Okay, so the Laplace transform without the exponential in it, without this part, is fairly straightforward, and I would expect that you would know that. Okay, but now I'm going to use the second translation theorem to find this plus 1 over s. To find this inverse Laplace transform. Okay, so this is basically fairly simple because a here is equal to -2. So basically what that is saying, if I think about the second translation theorem, it's saying wherever I see t in my solution here, wherever I see t, I'm going to replace that with t minus 2, and then I'm going to multiply the whole thing by the Heaviside function of at t minus 2. Okay, so well, the first term here, t e to the t, is going to become t minus 2 e to the t minus 2 plus sine of 2 times t minus 2. Well, there's no t's and 1, so that just stays as it is, all multiplied by the Heaviside function at t minus 2. Okay, so again, whenever you see one of these inverse Laplace transform problems where you have an exponential and you know you're going to have to use the second translation theorem, the first step is really just ignore the exponential altogether and find the inverse Laplace transform without the exponential in it, and then just apply the second translation theorem. And it's fairly simple. We're just subtracting yeah, anytime we see the t, we're just subtracting the value a there and multiplying by the Heaviside function. Okay, so if you're not 100% comfortable with that, just keep practicing. Keep sending me questions if you have them on that, and we'll work through it. Okay, so moving on to question 2 now. So question 2 is we're actually going to have to solve an initial value problem. So this is really where the use of the Laplace transform to solve these differential equations it becomes really helpful, right? Because, well, previously we've learned no other way that we can solve an initial value problem which has this Dirac delta function, this impulse function in it. So what I'm going to start with is take the Laplace transform of both sides of the equation. So, well, the Laplace transform of y double prime. Again, I kind of expect you might probably remember this by now, but if you don't, just go back to your table of Laplace transforms, and you'll see here that the Laplace transform of the second derivative of a function is equal to s squared times the Laplace transform of the function minus s times the first initial condition minus the second initial condition. Okay, so you've kind of got a life raft there if you need it. Okay, so this is equal to s squared times capital Y, where capital Y of s is equal to the Laplace transform of y of t. So s squared times y minus s times the first initial condition minus the second initial condition. Okay, and of course, both of these initial conditions are 1, so this is simply s squared times y minus s minus 1. The Laplace transform of y prime, again, you can refer to the table, but this is just simply s times y minus the first initial condition, which is equal to s times y minus 1. The only one that might be a little bit trickier is this Dirac delta function. So the Laplace transform of Dirac delta at t minus 2, let's just check the table for that one, shall we? All right, so let's see if we can find the Laplace transform of Dirac delta function. Okay, here we go. So the Laplace transform of Dirac delta function t minus t0 is e to the minus s times t0. Okay, so this is t0 here is 2. So we have e to the minus s times 2. So e to the minus 2s. Okay, so using those four Laplace transforms in our ODE, we get, well, the y double prime term becomes s squared times y minus s minus 1 minus 3y prime, so minus 3 times y prime. Y prime was s times y minus 1. Yeah. Let you scroll. S times y minus 1 there. Plus 2y, so plus 2y, that was the y term, equals the right-hand side was just the Dirac delta function, so we have this here. Okay, fantastic. And so what we need to do now, of course, is rearrange this function, or this equation for the term y. So on the left-hand side, I have an s squared there, I have a minus 3s there, and I have a plus 2. Now on the right-hand side, I've got e to the minus 2s, and if I take all these terms that do not have a y in them, to the right-hand side, then I get, what would that be, plus s, plus negative 1, plus negative, take away 3. So that's going to be minus 2, in fact. S minus 2. And therefore I can write y, my solution in s space is e to the minus 2s plus s minus 2 over s squared minus 3s plus 2. Okay, so I have a solution in S space, but of course now I want to invert that to get a solution in the other space, the T space. So I know I can already see that my denominator can be written as the product of two terms. So S plus 1, S, was it plus or minus? No, S minus 1, sorry, S minus 2. Because if let's start again, S minus 1, S minus 2. I'm still, after all this time, I'm still getting used to the tablet writing. Because if I take minus 1 times minus 2, I get positive 2. If I get minus 1 minus 2, I get minus 3. Okay, great. So I can write my y as e to the minus 2s over s minus 1, s minus 2, plus s minus 2 over s minus 1, s minus 2. Okay, well the second one's nice because the s minus 2's are going to cancel, and so this is just going to be s minus 2 plus 1 over s minus 1. So that second one there is just this very simple exponential. The first term I do have to use some partial fraction decomposition. So, well, let's write this. Let's write this down. E to the minus 2s over s minus 1, s minus 2, plus the inverse Laplace transform of 1 over s minus 1. So, of course, the second term here is just going to be the exponential, an exponential of t. Now, the first term here, well, I might need to use partial fractions on this, right? So 1 over s minus 1, s minus 2 is equal to a over s minus 1 plus b, s minus 2. Okay, well, if I cross multiply, I get 1 is equal to a s minus 2 plus b, s minus 1. Now let's try s equals 1. Then I get the b term is going to be 0, so I get a equals, what's going to be negative 1. If I use s equals 2, the a term is going to cancel, and I get basically b is equal to 1. So the inverse Laplace transform of, now I'm going to be 1 over s minus 2 minus 1 over s minus 1. That's easy, right? It's just some exponentials. So we're just going to have e of, first one will be 2t minus e of t. But actually, I didn't want the inverse Laplace transform of that. I wanted the inverse Laplace transform of the e to the, was it minus 2? Minus 2s times that. 1 over s minus 2 minus 1 over s minus 1. Okay, so that is going to be the Heaviside function, t minus 2, multiplied by this thing. And whenever I see a t in this equation here, I'm going to replace it with t minus 2. So e to the 2 t minus 2 minus e to the t minus 2. Okay, so that was that term. This term here was just going to, the inverse Laplace transform is just e to the t. So finally, I can write my solution, y of t is equal to u of t minus 2 e to the 2t minus 4 minus e to the t minus 2 plus that e to the t, that last term here. Scroll this term here. Okay, great. So now we've solved that ODE. Right, so we can move on now. So moving on to question 3. In fact, now we've solved all of the Laplace transform questions, and we're moving on to the from Unit 4, the systems of linear equations. So here we have a linear system of ODEs with constant coefficients. You can tell that because A is a constant matrix. There's no t dependence in there. It's homogeneous, right? So that's nice. There's no There's no particular solution we have to worry about. So if you recall, the way we're going to solve this system is finding the eigenvalues of this matrix. So we have to solve the determinant of A minus lambda I equals 0. In fact, the 0 vector. Okay, so what is that? Well, A minus lambda I, so that means we subtract lambda on the diagonal. So 1 minus lambda, 0, 1, minus 2, 3 minus lambda, 1, 0, 0, 2 minus lambda. That should be lambda. Okay, so that determinant of a 3 by 3 matrix, there are some zeros here, so this is going to be a little bit easier. So I'm going to get 1 minus lambda times this determinant of this thing, which is 3 minus lambda times 2 minus lambda. Okay. Take away minus 2, so plus 2, times the determinant of, let's delete those lines for the minute. The determinant of this other submatrix here. Okay, but that's going to be 0 because I get 0 times 2 minus lambda minus 0 times 1, so I get 0, plus 0 times something. So in fact, all I get here is this first term here. So I get 1 minus lambda times 3 minus lambda times 2 minus lambda equals 0. So in other words, it's quite easy to see that my eigenvalues, so lambda 1 is going to be equal to 1, lambda 2 is going to be equal to 2, and lambda 3 is equal to 3. So, well, it's kind of neat. So now I need to find so I've got 3 real distinct eigenvalues. I know that I can find then 3 distinct eigenvectors. So let's do this for lambda 1. So I have to solve the equation A minus lambda 1, so 1 times I, times the eigenvector k1 equals the 0 vector. So in other words, I'm subtracting 1 from the diagonal of A. So 1 minus 1 is 0, 0, 1, minus 2, 3 minus 1 is 2, 1, 0, 0, 1, times k1, k2, k3 equals the 0 vector. Okay, so let's read what each line is telling us here. Well, in fact, the top line and the bottom line are telling us the same thing. It says 0 times k1 equals plus 0 times k2 plus 1 times k3 equals 0. So this is telling us, this top line is telling us k3 equals 0. And in fact, so is the bottom line as well. So k3 equals 0. Okay, what about the middle line here? Well, this is telling us negative 2 times k1 plus 2 times k2 plus something about k3, but k3 is 0, so equals 0. And so this is telling us that k1 is actually equal to k2. So let's just take k1 equal 1, so therefore my eigenvector k1 is equal to 1, 1, 0. So there k3 equals 0, you can see, and k1 equals k2. Okay, so we got one eigenvector there. Lambda 2 equals 2. Well, again, I'm just going to go through this quickly because it's exactly the same process. A minus 2 times I, so we subtract 2 on the diagonals. So negative 1, 0, 1, 2, 1, 1, 0, 0, 0. Times k1, k2, k3 equals 0, 0, 0. Okay, great. So what is this telling us here? Okay, well, did I write that down correctly? Hang on. 1, 0, negative 1, 0, 0, 0. Okay, great. I think I missed, should be a negative 2 here. Okay, so the last line there is telling us no information because it just says 0 equals 0. The first line, though, is saying negative k1 plus k3 equals 0, or in other words, k1 equals k3. The second line there, this is saying 2 times k1 plus k2 plus k3, but k3 equals k1, so I'm just going to write that as k1 equals 0. So what is that telling us? That is telling us something that's different in my notes. Sorry about that. I just realized I missed a -2 here. So this should be -2 times -2 times k1 plus k2 plus k1. So this tells us that k2 equals k1. So in fact, k1 equals k2 equals k3. So we can write down the second eigenvector as 1, 1, 1. Because k1 equals k2 and k1 equals k3 as well. k3 equals k1 as well. Okay, so then lambda 3, which was 3, again, we'll just write down the matrix here. So we take away 3 from the diagonals now. So we get -2, 0, 1, -2, 0, 1, 0, 0, -1 times k1, k2, k3 equals the 0 vector. Again, this bottom line here is telling us that k3 equals 0. What else? This top line here. Well, in fact, both these two lines here are telling me that -2 times k1, k3 is 0, right? So equals 0. So k1 equals 0 as well. It doesn't tell us anything about k2, so k2 can be anything. So let's take our third eigenvector to be 0, 1, 0. Therefore, my general solution to this homogeneous system is equal to C1 times K1, which was 1, 1, 0, times e to the lambda 1t, well, lambda 1 was 1, so we get t, plus C2 times K2, which was 1, 1, 1, times e to the 2t, plus C3 times 0, 1, 0, e to the lambda 3, which was, what was lambda 3? 3? Yep, 3t. Okay, so that was actually case 1 that we studied in class, and fairly easy to solve, I think. The hardest thing is finding the eigenvalues and eigenvectors without making a mistake. Okay, so let's move on to the last question here, which is 3b. So we have a non-homogeneous system of linear equations. The first thing we were asked is to write the non-homogeneous system in matrix form, so let's do that. So let's look at this vector xy. Let's let A equal, well, the first equation we have 1x and -1y. The second equation we have 1x and 3y. Okay, and we also have a non-homogeneous term here, right? +1. So f is equal to 1, 0, and therefore we have x prime equals a times x plus f. So that is the system written in matrix form. Okay, so fairly straightforward. The second part, find the complementary solution, i.e. the solution to the homogeneous system. So for part II, we're trying to find x prime equals a times x. And again, remember to do that, we have to find the eigenvalues of a. Okay, great. Well, you can do that by solving that determinant, but I also kind of like to say that lambda 1 plus lambda 2 equals the trace of a. Okay, well, the trace of a is 1 plus 3, which is 4. And lambda 1 times lambda 2 is equal to the determinant of a. Okay, what is that? 1 times 3 is 3, minus 1 times -1, so plus 1 is also 4. Okay, so we need two numbers that add to 4 and multiply to 4. Well, that's probably not too hard to see. That's 2, right? So lambda 1 equals 2, multiplicity equals 2. So now actually we've got a repeated eigenvalue here. Because two numbers that add to 2 and also multiply to, so two numbers that add to 4 and also multiply to 4, it has to be 2 times 2 and 2 plus 2. Okay, so here I've got an eigenvalue which is repeated, multiplicity 2, so I need to find the associated eigenvector here. So a minus 2 on the diagonal, so a minus 2i times k equals 0. Okay, what is a? So 1 minus 2 is negative 1. We had a 1, we had a negative 1 there as well. 1, 1 times K1, so K1, K2 equals 0, 0. So, well, both of these lines, in fact, are telling me, so the first line is telling me negative K1, negative K2 equals 0. The second line is telling me K1 plus K2 equals 0, and they're both telling me basically K1 equals negative K2. Or in other words, my eigenvector rather, is 1, negative 1. Okay, great. Unfortunately, I'm missing an eigenvalue, right? I'm missing an eigenvalue here. I've got two I'm missing an eigenvector. I've got two eigenvalues here, but it's repeated, but only one eigenvector. So now I need to solve the equation a minus 2I times K2 equals K1, where K1 is this one we've just found. So now I'm solving negative 1, 1, 1 times K1, K2 equals 1, negative 1. Okay, so now we can actually get some information out of here. So which line should I start? The first line is saying negative K1, negative K2 equals 1. Or in other words, K1 is equal to negative K2 minus 1. Negative K2 minus 1. So let's just choose K2 to be 0, then K1. So if I choose K2 equals 0, then K1 is going to be negative 1. So my second linearly independent eigenvector is negative 1, 0. So therefore my general solution to my, my complementary solution, because I was only solving the homogeneous case here, is equal to C1 e to the 2t, because 2 was my eigenvalue, times the first eigenvector 1, negative 1, plus C2 e to the 2t times t times that same eigenvalue, plus that second generalized eigenvector. Okay, so there's my complementary solution. Again, it really relies on you knowing the three different cases that we have to solve for these systems. Okay, the next two parts of my question say find a particular solution to the non-homogeneous system and then find the general solution. Well, the general is just the complementary plus the particular, right? Okay, but we want to find a particular solution here. So I. So we want to find xp here. So my particular solution, well, my function, my non-homogeneous function was just the constant vector 1, 0. So I'm just going to try xp equals a, b, where a and b are just some real numbers. So they're in the real numbers. xp prime then, of course, is equal to 0. And I can use those in my ODE. So xp prime, which is 0, 0, and 0, 0, equals a. So what was a again? It was 1, negative 1, 1, 3, times xp, which is a, b, plus f, which is 1, 0. I need to solve this system for a and b. Okay, so, well, what does that first line tell me? The first line is saying 0 is equal to 1 times a minus 1 times b plus 1. The second line is telling me 0 is equal to 1 times a plus 3 times b plus 0. So, well, which way should we do this? We could say that from the first line here, this tells us that a is equal to b minus 1. If I use that in the second line, it says 0 is equal to b minus 1 plus 3b, which of course is b plus 4b minus 1, or in other words, b is 1/4. Okay. A is b minus 1, so a is 1/4 minus 1, which is negative 3/4. So our particular solution, xp, is equal to minus 3/4, 1/4. And therefore our general solution is equal to the complementary plus the particular. Okay, well this was C1 e to the 2t 1 negative 1 rather, plus C2 e to the 2t t times 1 negative 1 plus that generalized eigenvector there. So there's my xc from before, plus xp, which is negative 3/4, 1/4. Okay. So again, there's probably quite a lot of work in that test. If you have any questions, let me know. Keep practicing, and yeah, let me know how you're getting on. Thank you.